Welcome to today's class on vector analysis. Today we discuss the method of Lagrange multipliers. So before discussing method of Lagrange multipliers, we develop some theory behind this method to find constrained extrema. So first we discuss orthogonal gradient theorem. The orthogonal gradient theorem says that suppose that f of xyz is differentiable in a region whose interior contains a smooth curve C given by r of t equal to g of ti plus h of t j plus k of t k. If p naught is a point on C where f has local maximum or minimum relative to its values on C, then del f is orthogonal to C at p naught. We prove this theorem. The idea of the proof is that we show that del f is orthogonal to the velocity vector to C at p naught. Proof: we show that del f is orthogonal to the curve's velocity vector at p naught. So we have C is given by r of t is equal to g of ti plus h of tj plus k of tk. That is, x of t is equal to g of t on the curve, y of t equal to h of t on C, and z of t equal to k of t on the curve C. Therefore, the values of f of xyz on C is given by f of x of t, y of t, z of t is, x of t is equal to g of t on the curve, y of t is equal to h of t on the curve, and z of t is equal to k of t on the curve. So this is equal to f of g of t, h of t, and k of t. F of g of t, h of t, k of t. We have at any point p naught, f has a local maximum or minimum relative to its value on C, df by dt is 0. So at any point where f has a local maximum or minimum, df by dt is 0. And you consider df by dt. df by dt is dou f by dou x into dx by dt plus dou f by dou y into dy by dt plus dou f by dou z into dz by dt. On the curve C, x is g, y is h, and z is k. So this is equal to dou f by dou x into dg by dt plus dou f by dou y into dh by dt plus dou f by dou z into dk by dt. So this is actually equal to dou f by dou x I plus dou f by dou y j plus dou f by dou z k dot dg by dt I plus dh by dt j plus dk by dt k. So this is equal to, this quantity is del f dot, this is the velocity vector to the curve C. So it is del f dot v. And you know that at extremum points on C, we have df by dt equal to 0. Therefore, del f dot v equal to 0. So this proves orthogonal gradient theorem. Therefore, if f has a local maximum or local minimum at P naught, then del f is orthogonal to velocity vector v, velocity vector at P naught. Therefore, del f is orthogonal to C at P naught. Orthogonal to C at P naught. So this proves orthogonal gradient theorem. Now, by dropping set terms in the above theorem, we get a corollary to the theorem for the case of functions of two variables. At the point on a smooth curve, r of t is equal to g of t I plus h of t j, where a differentiable function f of xy takes on its local maxima and minima relative to its values on the curve del f dot v equal to 0, where v is dr by dt. So the proof is similar. We have on C, f of xy is f of g of t h of t, and at extreme values on C, we have df by dt equal to 0. But df by dt is dou f by dou x into dx by dt plus dou f by dou y into dy by dt. So this is equal to dou f by dou x into dx by dt is dg by dt plus dou f by dou y into dh by dt. So this is equal to del f dot v, where del f is dou f by dou x into I plus dou f by dou y into j, and v is dg by dt into I plus dh by dt into j. Therefore, at extreme points on C, del f dot v is 0. Therefore, del f is orthogonal to v at a point of extrema, at point of maxima and minima on C. Therefore, del f is orthogonal to C at P naught, where P naught is a point of local extrema. So this proves that corollary. Now we state method of Lagrange multipliers. Suppose that f of xyz and g of xyz are differentiable. To find the local maximum and minimum values of f subject to the constraint g of xyz equal to 0, find the values of x, y, z and lambda that simultaneously satisfy the equations del f equal to lambda times del g and g of xyz equal to 0. For functions of two independent variables, the conditions is similar but without the variable set. So this is the method of Lagrange multipliers to find the maxima and minima in the case of constrained extrema. So we'll discuss a problem. So we solve this problem using method of Lagrange multipliers. So this is an example solution. So we have to find the points closest to the origin on the hyperbolic cylinder x square minus z square minus 1 equal to 0. A way to find the points on the cylinder closest to the origin is to imagine a small sphere centered at the origin expanding like a soap bubble until it touches the cylinder. So you consider a sphere which is expanding from origin like a soap bubble and it just touches the hyperbolic cylinder at these points. Then the points at which the sphere touches the hyperbolic cylinder will be the point on the hyperbolic cylinder which is closest to the origin. That is our way. So at each point of contact, the cylinder and the sphere have the same tangent plane and normal line. Therefore, if the sphere and the cylinder are represented as the level surfaces obtained by setting f of x by z, that is equal to x square plus y square plus z square minus a square, and g of x by z, that is equal to x square minus z square minus 1 equal to 0, then the gradients del f and del g will be parallel where the surfaces touch. So at the point of contact, you know that f is x square plus y square plus z square minus a square. So the direction of del f will be like this. This will be the direction of del f, you see, because it is expanding outward. And at the point of contact, if you are considering the surface to be oriented in this direction, then the del g will be in this direction, in the outward direction in any way. So this is your del f and this is your del g, and you can say that del f is equal to some lambda times del g, or we can say that these two vectors are parallel, maybe in opposite direction, no problem, it is parallel. So therefore, if the sphere and cylinder as are represented as the level surfaces obtained by setting f of x by z equal to 0, g of x by z equal to 0, then the gradients del f and del g will be parallel where the surfaces touch. At any point of contact, we should therefore be able to find a scalar lambda such that del f is equal to lambda times del g. So we use Lagrange multiplier here. Here f of x by z is x square plus y square plus z square minus a square, and g of x by z is x square minus z square minus 1. Therefore, del f is equal to I dou f by dou x plus j dou f by dou y plus k dou f by dou z. So that is equal to dou f by dou x is 2x, dou f by dou y is 2y, and dou f by dou z is 2z. So this is 2xi plus 2yj plus 2zk. So this is del f, and del g is I into dou g by dou x plus j into dou g by dou y plus k into dou g by dou z. So this is equal to 2xi plus 0j minus 2zk. Therefore, del f is equal to lambda times del g, implies del f is 2xi plus 2yj plus 2zk, that is equal to lambda times del g is 2xi minus 2zk. So this implies xi plus yj plus zk is equal to lambda xi plus 0j minus lambda zk. Now we solve for lambda x, y and z. So this implies x is equal to lambda x, y equal to 0, z equal to minus lambda z. So we have xyz is a point on the hyperbolic cylinder x square minus z square minus 1 equal to 0. We have no point on the surface x square minus z square minus 1 equal to 0 has x coordinate 0. Therefore, x is not equal to 0. Therefore, from the equation from x is equal to lambda x, we have lambda equal to 1. And when lambda equal to 1, we have z equal to minus z from this equation, from star. If you take this as equation star, from star. So this happens only if z is 0, which happens only if z equal to 0. Therefore, we can conclude that the point we search on x square minus z square minus 1 equal to 0 closest to the origin will be of the form x 0 0. And since x 0 0 is a point on x square minus z square minus 1 equal to 0, we have x square minus z square is 0 minus 1 equal to 0. This implies x square is 1. So this implies x is plus or minus 1. Therefore, the points on the hyperbolic cylinder x square minus z square minus 1 equal to 0 closest to the origin are 1 0 0 and minus 1 0 0. And the shortest distance from origin to the hyperbolic cylinder is square root of 0 minus 1. For example, if you are considering this point 0 minus 1 the whole square plus 0 minus 0 the whole square plus 0 minus 0 the whole square. So this is square root of 1 square. So this is 1 unit. So this is the solution to that problem. The points on the hyperbolic cylinder x square minus z square minus 1 equal to 0 closest to the origin are 1 0 0 and minus 1 0 0. You may verify it using GeoGebra, and that is a home assignment for you. And that's all for today. Have a nice day.